we finish with functionals and start to study the operators. So first theme. But in spite as it was in linear algebra, in linear algebra usually investigates and considered so-called Hilbert adjoint operators. But first I give the definition of the Banach adjoint operator. Okay. First definition that x, y are Banach spaces and A is the bounded operator from x to y. Bounded operators from x to y. If we say bounded, it is of course linear. Yes, it is of course linear. So adjoint operator A prime, I denote it as S prime, not as A star, in order to differ it with the Hilbert adjoint operator. So it is Banach adjoint operator. Is operator from following spaces to the following spaces. It acts between the adjoint operator, between dual spaces, so it acts on functionals. And the definition for any f from y star, for any x from x, let's understand what it happens. We act by the operator on functional f, which belongs to y star. So we go to the x star. So it is new functional from the x star. And we can add on by this functional on the element x. Yes? And the definition is that it is f a x. And we define the left side through the right side.
In differential geometry, there are push forward and pull back map.
Yeah, maybe, yes. Yes, similar. And some remarks. I think it's obvious that A prime is a linear operator. Yes, because the space of functionals is linear, and we define the actions of functional pointwise. So is linear. Is it clear? Oh, it's okay. And second, it is not obvious that it is bounded, but we just prove it. Moreover, we prove the following statement. The norm are equal. Norms are equal. Proof. By definition, it is supremum all over functionals f with the unit norm. I don't repeat from what space the functional f we take. It's from these lines we can see for shortness. So this is a functional, yes? This is a functional, so we following we define the norm of the functional. The norm of the functional is and we have two supremums. Here the supremum all over x with the unit norm, and the outside supremum all over f with the unit norm too. And here I take away the norm because it is the action of the functional, it is a number. And the absolute value of this number is, we take the only modulus. Then by definition, you can rewrite it in the form and then you can use the multiplication inequality for the norms. Multiplication inequality means that it is less or equal double supremum norm f multiplied on norm ax. This gives us 1 because we take functionals with the unit norm, and this gives us the norm of A. This is. Yeah. So we prove that it is bounded. And if you analyze our calculation, we see that we have only one place where we have inequality in this by multiplication. Inequality. In other places we have equalities. So let's remind the first corollary from the Banach theorem. Banach theorem. For any x which is not 0, there exists functional from x star, the norm of the functional equals to 1, and f of x equals to the norm x. If our operator A, the original operator A, is 0, so here we have only the 0, and any linear functional on 0 gives us the 0. So we immediately obtain that the adjoint operator is 0, too. So the norms are coincide, it is a trivial situation. So interesting situation when A is not 0, so if it is not 0, there exists x for which AX is not 0. And yeah, use this corollary from the element AX. If A is not 0, then exists x such that AX is not 0. Moreover, we take the supremum, all of elements AX, yes? And what we can say about this? For this element, there exists functional with the norm 1, and this functional just is from this space because AX belongs to the Y. AX belongs to the Y, so F we must take from the dual to Y space, Y star, such that F on AX gives the norm of AX. So this value changed to the norm AX. For this functional. For any arbitrary function, we have the inequality, but we have at least one functional, but there are a lot of. There exists at least one function from this space, from this set, from the unit sphere, which gives us this value, the norm of AX. And after this, we must take only supremum for all x which equals to 1, and then we obtain just equality that it is equal to the norm A. Is it clear? This gives us equality in this. Let's one example of calculating of these operators. The typical example of Banach operators, it is LP, where P is not equal to 2, or the space of continuous functions. So I consider operator A from continuous function on interval 0, 2 to the same space. Continuous function from the 0, 2. What is the rule of this operator? That is identity on the half of the interval. And then we must obtain the continuous function. And then it make it constant. So it is clear that the image of operator is a continuous function. So we some picture. Let's some function f, and this is 1, this is 2, and our operators changes to this function. Some another color. So, question: what is the adjoint operator? What is the adjoint operator? It is important to change a proper language to describe the action of the operator. If you want to obtain the answer, you must only describe the action of operator on functionals, yes, on functionals. But what we know about adjoint or dual space to the space of continuous functions? So first step, A prime x from this space to this space. Yes? For example, if we take element G capital, we obtain double V capital from this. It is functionals. But by the Ries theorem, it is Ries theorem 2 on description of the functionals on continuous functions. It is functions of bounded variations, yes? We know that these functionals act as so small capitals is for functions. Large capital letters is for functionals. Small letters for corresponding functions. So it corresponds functions double V small, and we know that on another functions it is the Riemann Stieltjes function. Yes? So I describe the action of A prime, not by action on functionals, but by actions on the functions of bounded variations. It is more simple. But if you can describe how change the function of bounded variation, so of course you know how your operator acts. Yes. So let's do it. So we start from this. But by definition, how you can rewrite this? By definition, how you can rewrite this object? F8, yes. It is not G of AF. Yes? So it is AF of T dg. But we know how this looks like by this rule. By this rule. So you can write it in two parts, divide the integral in two parts. On interval from 0 to 1, what we can write? It is as identity. As identity, yes? So we write it as ft dg plus f1. F1 is constant, so I take away it outside the integral and write 0, 1 dg.
But sir, why is a prime g of f equal to g of af?
It is a definition of a joint operator.
It's okay. It's not.
It is just definition of a joint operator. We began our lecture from the notion of a joint operator. It's just a definition. We define a joint operator as following. It is a Banach joint operator. It's not a Hilbert joint operator. This is just I define the image of operator, works on functional G, obtain functional W. That's the definition of our functional W capital. We write it via function of bounded variations. This is a definition of a joint operator. Here I put the definition of our operator A, the example of operator A, and divide integrals in two parts. And f1 is constant, so I take away outside the integral.
So just to be on the same page
Okay.
for the notation, a prime is the joint.
Is Banach a joint operator to A? Yes. A. And now what you can write? It's just I remind we integrate on the interval 1, 2, so starts from 1 to the right. And we know that our functions g and w are from space BV0. So they are continuous left continuous in the interior points, but not right. And this formula must be the same as this formula. So our goal to describe the functional W capital via the functional G capital. It is the same to describe what happens with the function G small. So we must describe in what function W small it goes. Yes? So let's try to. So only compare by comparison with this formula to this formula. Is it clear that on interval t coincides with g at t if t belongs to 0, 1? You see this here. W on whole intervals from 0 to 2. And here we have integral part dg from 0, 1. So they are coincide. And we have f of 1, which integral gives us, which function g gives us a value at a point. A jump. A jump. What is the value of this jump? The value of jump, just this coefficient. Just this coefficient. So, some picture. For simplicity, I draw the continuous function. But we know that in BV can be. Let's see that this is function g. This is 1. So for this place, our function W is the same. Just like yellow something. W, yes? Here value is g of 1, yes? And now you must, and there are no another integral paths, yes? There are no integral from 1 to 2. No. What it means? It means that our function W must be a constant. Must be a constant. Because we have no integral. This is coincide with this. So function W must be constant after 1. After t equals to 1. What the constant? The following constant, that the jump from this point to this point. And our function is continuous to the left. What is the value of this jump? Just the coefficient for f of 1. So this is step equals g of 2 minus g1 plus 0. So in my example, this doesn't matter 1 plus 0 because I draw a continuous function. But for example, your function g can be discontinuous at point 1. So you can calculate the height of this jump. So this is the value of this jump, and this is value equals to what? G of 2 minus g minus plus 1 minus g of 1. So you can write the answer g of 2 minus g plus 1 minus g of 1. T belongs from z1 to. That is the answer. That is the answer for calculations.
So can you explain the notation here, what you wrote here, g1 plus 0?
It is right limit, 1 plus 0, it is right limit of function g. From the space, therefore from the BV0, and in space BV0, the functions are continuous from the left. So when we calculate this integral, we obtain that this equals, we integrate differential of g. So it equal to this difference. It is the coefficient for f of 1. So this is coefficient tells us what must be the jump in point 1. It equals, so I need to write the right limit, because here I obtain the right limit for function g.
Okay.
Is
So
it-
it's basically defining the right
Yes.
right limit.
Yes.
1
Yes.
plus 0.
Yes. So we describe the action of functionals, or we describe the actions of adjoint operator on functionals of bounded variations. But of course, we can reconstruct the acts of this function operator on the functionals, because any functions of bounded variations represents for us a function. Yes. So it. I understand it was not easy to understand how it acts, but it is not difficult. So it is sufficient to solve 1, 2, 3 problems to calculate directly some operators and understand. So let's go to the Hilbert, more typical situation, more useful for you, so-called Hilbert adjoint operator. What we have? Definition. H is Hilbert space. A is bounded operator in H, but later we consider not bounded operators and try to construct the theory of adjoint operators for not unbounded operators, but just now it is a bounded operator. A star acts from H to H. It is more convenient. Why we can do it? I described the situation of Banach adjoint operator. It acts in another space. It lives in another space. It lives in space for functionals. But we know there is theorem. For a short remark, A, H, H, A prime. But it is it is very strange situation because to consider you can consider in Hilbert space a Banach adjoint operator. It's acts like this by common rule. But we know by Ries's theorem, that these functions, these spaces, are isometrically isomorphic. So by this you can define another adjoint operator which acts in the same space. It is more convenient, such that the diagram is commutative. So the diagram is commutative. You construct isomorphism and you obtain the adjoint operator here. But I defined it in another way. I defined it in a way more usual for linear algebra. Such that for any x, y from H, a x, y equals x, a star, y. But it is, if you're attentive, you can ask some questions. Why this equality defines some operator? Why left side of this equality defines some operator A star? Maybe it does not exist. In a linear algebra, it's very simple. You choose the basis, you write operator as matrix, write this equality, and you see that matrix of operators change to what matrix? Transposing and conjugate, complex conjugate. So and you say that let this transposing and conjugate matrix be the matrix of a new operator, and we name this operator A star. But in infinite dimensional spaces, it is not the same way. More, if your space is separable, we know that it have countable bases. So we can obtain the infinite matrix and can describe the adjoint operator by if a space is not separable, what is the way to describe the adjoint operator? So you understand the question, why this quality defines the operator. But it is we have a Ries's theorem. Ries's theorem is a powerful instrument. So what we so I show that there exists operator. Let's fix A is given. A is given. Let Y is fixed. I can consider this value as a functional. What you can say about function, this functional? It is linear. It is linear, and by Cauchy-Banachowski inequality, you can write this inequality, and then the multiplicative inequality shows us that this functional is bounded. And these values is the estimation on norm of operator. Or functional. So f is bounded. Our goal is not to calculate the precise norm. It's sufficient only to show that it is bounded. By Ries's theorem, what we know about bounded functionals? There exist element z. So by exists z from H such that this functional fx looks like scalar product xz. So we immediately obtain that axy can be presented as following. But linear, the scalar product is semi-linear for the second arguments, but y and z simultaneously stay on the second place. So we conclude that the z linearly depends on y. Yes?
So can you explain it again?
That linear depends on y. Now, if you consider, so we take only one fixed element, but imagine that you write ax alpha y1 plus beta y2. By linearity of this, you can rewrite as alpha conjugate ax y plus beta ax y2. By any fixed elements, you can write it as alpha x z1 plus beta conjugate x z2, and then you can write it as this calculation is clear. So we immediately obtain that linear combinations of y's corresponds to the linear combinations of z's. So it means that this is a linear operator. It is a linear operator, and we define this linear operator as a z equals a star y. So we defined this linear dependence of z on y in the following way. Hmm? Yes, we just show that it is bounded. That it is bounded. Moreover, the norms are the same. So lemma let A is bounded in Hilbert space. Then the norm A can be calculated as supremum on two spheres. Can be calculated as supremum on two spheres. Of so-called semi-square form of operator. Not quadratic form, but semi-square form. Proof. First, Cauchy-Bunyakovsky inequality, yes, and then multiplicative inequality. And take the supremum on two spheres, supremum of x and for y with unit norm. Second, if I consider not all y's, but some special cases of vector y's. Of what kind? Of such kind. If operator is not zero, then there exists some vectors x for which it is not zero. If we want to calculate supremum, we need to take such a vector x that ax is not zero. If operator a is zero, this situation is trivial. Of course, the adjoint operator is zero too, yes? Because if operator a is zero, here always zero. And of course, if I take only such y's, we have this inequality. And put it as ax divided on ax. What leaves from this scalar product? ax on ax, it is ax norm square, and we divide on norm ax. So we obtain of course it is equal to norm, because these do not influence, these demands do not influence on the operator A, if we want the supremum. So I think we prove an equality. We prove the equality. Immediately corollary is that I can name it theorem, but it is just corollary. Norm A coincides with norm A star. Do I need to write something for proof of this statement? Is it clear that the orders of x, y, here x doesn't influence on this definition? And so proof. Is it sufficient? These two equalities. The supremum for x, y, for this gives us the norm A by the lemma, and supremum for x, y here gives us the norm y star. And very important notion, self-adjoint operator. What means self-adjoint operator? A is self-adjoint if A star equals to A, yes. If A equals to A star. Your program is geometry and quantum fields. Yeah? The axiomatic of quantum mechanics. For any observable corresponds some self-adjoint operator. The values of this observer which can obtain due experiment is just the spectrum of this operator. Yes. The study of spectrum will begin later. So self-adjoint operators are really important. Then we have a lot of operators. Yes.
Yes, and they have a kind of real numbers. Like it's
The spectrum of self-adjoint operator is real.
yes, exactly.
Yes.
Because it reflects a physical reality.
Yes. But there are a lot of operators which are not self-adjoint but have real spectrum first. And there are a lot of self-adjoint operators which do not correspond for any observable. So it's in a book, The Jokes of Physics, so there exists some not observable objects which correspond for these operators. So some examples. Let's consider, so I don't write the space, but by definition, in what space you can define the self-adjoint operator? Only in Hilbert space. So remember that Banach's adjoint operator acts in another spaces, in space of functionals. And you can consider Banach adjoint operator in a Hilbert space too, but it must work on the functionals. So before examples, what you can say about this operation? What is the answer? And what is the answer for this? Alpha conjugate. So it says algebraist, so variant functor, covariant functor. it's in algebra of categories there are the notion of functor. It's the same as how change the when we change the basis, how change the coordinates of the vector
Yes.
in one law, and how change the coordinates of functionals in finite dimensional space in another way. So it is the same because it acts on the functionals. So it's so what is you have tensor of type PQ, yes. So it is linear on for P plus Q objects. By for first P objects, coordinates of tensors or tensor numbers change if we change the basis on the one law, and for the second group of object Q in another law. So you can imagine tensor as direct sum, direct product of P vectors and Q covectors, Q functions. So it is the same of functors. So examples. First, L2. These operators are always appears in pair. Why? Shift to the right and shift to the left. I use the typical hour notations for not to describe this. What you can say about find the adjoint. Yes, the answer that AR is left shift and is right shift. Oh, it is. Moreover, for any operators bounded, what you can say about this?
Itself.
Yes, but for unbounded operators is not correct. It is not. For unbounded operators is not true. We consider it later. We consider it. We have some lectures in the future for unbounded operators, and we will see that for unbounded operators it is not true. Is it clear, or must something calculations?
No, it makes sense that unitary.
Why it is not unitary? No, it is not unitary. The shift to the left and shift to the right are not unitary.
But if it's
You-
double-sided L2.
Oh no. For example, shift to the right, it preserves norm. But the definition of unitary operator, it is a bijection which preserves norm.
But I mean,
And shift to the left, it can make norm less.
but if it's a two-sided, it's
If you consider two-sided space L2 two-sided, so the shifts to the right and to the left are unitary, yes, in two-sided L2. In two-sided L2. So it is second example. What is the adjoint operator for multiplication on sequence? Alpha is a bounded sequence. Alpha is sequence alpha 1, alpha 2, alpha n, and it is from infinity for boundedness of operator. What is the adjoint operator for this operator? It is a typical, it is so-called toy examples, because they are very simple.
Would be multiplication by the conjugated sequence.
Yes, I can write the answer in a shorter way as follows. It is real. It is true. Yeah, it is multiplication on conjugate sequence. It is. Let's one solve this. By definition, this, and I can rewrite it as. And this is not the action of operator. It is from the scalar product. And here, just here, the action of conjugate operator, adjoint operator. So it is x, a star, y, and we see this answer. When it is self-adjoint, so these operators are not self-adjoint. But when the operator of multiplication,
The sequence is real.
Well, the sequence is real. Sequence is real. Let's say give some more definition. I use another letter because I want to define the unitary operator. So it is the first letter of the word unitary. Unitary. And second, for any x, y from H, so, for example, A right is not unitary because it is not biaxial. It is not surjective. But in two-sided L2, these all operators are unitary. Why I give this example? Ask this question for this. When this operator is unitary? When this operator, multiplication of the sequence, is unitary? We don't consider the notion of inverse operator, but soon we consider the inverse operator. These two, if operator is biaxial, it has bounded inverse operator. It's so-called Banach theorem. If it is biaxial, it has bounded inverse operator. And if we see that it is fulfilled for all functions, you can rewrite it as it is valid for all x, y. So what you can say about this? It is identity, yes? It means that adjoint operator is coincident with inverse operator. It is equivalent definition of unitary operator. It is an equivalent definition of unitary operator. From this, you easily obtain the answer for multiplications. Because a unitary operator, we know that it is alpha k star, and inverse operator, you must divide on alpha k. This is adjoint operator, this is inverse operator. And of course, for inverse operator, alpha k is not zero because we must have biaxial. So we immediately obtain that alpha k have absolute value 1. Maybe complex, but so alpha k is something with some angle theta k. So this operator is unit. And one more, so another operators we consider on seminar, yeah? And another application of adjoint operator, self-adjoint operator. Projectors. Let X is Banach space and X0 is subspace. Let's be closed subspace. Later I try to explain why it is more good situation. Is closed subspace. Do you remember the problem of the closed complement? We have division on and exist x1 is close to such that x can be represented as direct sum. It is direct sum. So x, any element x can be divided in two components, in sum of two components of the corresponding subspace. Then you can define the operator of projections or projectors. Projector. P is projector. Projector, yeah? On x0 along x1, because this space is not unique. x1 is not unique. You can define different projectors, even in two-dimensional situation. Even in two-dimensional situations, the projector is not unique. So all subspaces are important. So it is defined as x0, as x1. So it gives us first component. It is geometric definition of projectors. And you can obtain in easy way the algebraic definition of projection. It is so-called idempotent. Algebraic definition, it is the same as the second power is the same operator as P. Because you see that, huh? It's definition of projector. It is geometric definition. I give this with the help of subspaces. And this is algebraic definition. They are equivalent. You can define the image of P is x0 and the kernel of P x1. And then you show that you obtain all space. Why I take this? Because if you see the definition, we do not use these properties, the clauses of operator, of subspaces. We can define it without any clause. Yes, if you have a direct sum, if you have the direct sum of any subspaces, you can define projector. You can define the projector. I give these demands, these assumptions, only for one thing, the theorem. Projector is bounded if and only if all two subspaces x0 and x1 are closed. If you want to work with bounded projectors, you need to have closed subspaces. Yes, it is. In topological we say continuous, yes, but in normal space we can say bounded operators. When we consider Banach theorem on inverse operator, we can discuss it. We can obtain from the Banach inverse theorem. An example that this space is not unique. Let X is I can take x1 as linear span of this vector, but I can consider x1 prime as linear span of this vector. Both sums are direct. So you have two-dimensional space. You take x0 as here, x1 here, but x1 prime here. The sum of these two subspaces is all R2, and the sum of these spaces is 2R2. Yeah. So why we say this on x0 along x1? Because this space is important too. Is important too. And all this situation can be considered in Hilbert space. All this situation can be considered in Hilbert space. But in Hilbert space, what is complement is more convenient. And what we have additional geometric comparison of subspaces. We have orthogonality. So let's solve one easy problem. So theorem. let H Hilbert space H equals to the sum of the closed subspace closed then we define projector. Yep. On H0 along H1. Then what is the answer? So among all divisions or all representation in direct sum, we have the orthogonal complement, yes? When we take H1 as H0 orthogonal. In terms of operator, self-adjoint. Self-adjoint. And you understand that we take closed subspaces because we want to deal with bounded operators. So self-adjointness of projectors. What?
But also the idempotentness
Of this, yeah, this is you can consider this as take as definition of projector. It is just a definition of projector in a general situation.
But I mean, do we need to require it in that case?
Because it is projector. So if it is projector, so this is it is a projector with of course. So orthogonal projectors is two conditions: these conditions and this condition. Orthogonal projector. Because this is projector and this is orthogonal projector. This is orthogonal projector. So let's prove it. It is easy theorem. It's about one line and for all implications. So it is good remark. I give it as remark. It is valid because it is projector. Because it is projector. So in what direction we first prove? From dot to window, from window to door. What? Like this? Okay. So we must change. So it is projector for one more remark. The additional operator is on H1 along H0. Additional operator identical minus this identical operator, not EE set but I. Is it clear? You may prove it in different ways because, for example, x equals x0 plus x1 by definition of geometrical approach, and you can see that x minus x0 equals x1, and this is I minus p x on x x1. So you see that this operator gives us the second component, but the order of components doesn't matter, which is the first and which is the second. Another way. You can directly calculate this. It is equals to pi, p. So the square equals to the same operator, so it is projector. So it is preparing work. Yes, it is a preparing work. It's
Any operator that satisfies p square equals to p means
What?
Any operator p satisfied p square equals to p is
Only projectors.
No other.
No.
Just like
Shift to the right is not equals to this. For example, because it have only one zero component and it has two first zero components. Moreover, you can invent the operator which is not zero but square is zero. Finite dimensional situation Jordan block with the zero on the diagonals, for example. And you can invent such operators in infinite dimensional situation. Operator is not zero, but the square of operator is zero. Okay, but we do not start the proof. only some preliminary remarks, yes, of general situation. So what we need to show, if operator is self-adjoint, we must show that x0 orthogonal to any y1, yes? So from x we obtain x0, from y we obtain a y1, it is from h0, it is from h1. Our goal shows that x0 equals to 0, yes? Why these subspaces are orthogonal? This is what we need to show. But x0 is a result of action of operator P. But y1, we say that it's additional operator. It is just and your operator is self-adjoint. If it is self-adjoint, you can put it on the right argument. So we immediately obtain that it is equals this. And if you take away brackets, you see that this is that's all. So self-adjoint gives us orthogonality. And it's clear. So okay, good. Second direction, I take it away. We must check that we can put operator from left argument on the right argument, yes? So let's do it. For arbitrary x and y. By definition of projections, it is equals to this scalar product, yes, because it is projective. Then we continue this scalar product in the following way, because scalar product of x0 and y1 is 0 because they are orthogonal. Then you can put the zero sum, because x1 on y0 is 0. So you can write it as x p y. By definition. That's all. That's all. Okay. And more addition notation. What operators are normal operators? Yes. So H is Hilbert. A bounded operator and A is normal if examples of normal operators. Examples of normal operators. Hmm? Because it is self-adjoint. The any self, but I defined it as for bounded operators. Hamiltonian is not bounded, but if it is closed operator, it is normal, of course. All self-adjoint operators are normal. Yes. Examples. Any self-adjoint operator is normal. If operator is unitary, what you can say? If it commute with, because it's identity, yes? It's identity. Is this operator, we know when it is self-adjoint, when alpha is real, alpha k is real. We know when it is unitary, when the absolute values of alpha k is unit, is 1. But we can consider arbitrary operator of multiplications. In any case, it is normal. In any case, it is normal because how you can write the result in short way. Yes, it is multiplication on absolute values of alpha k square. It is normal too. Then you can consider operator of multiplication on function in not in L2 small but in L2 capital. Let's consider it on seminar. But example of not normal operator. So the shifted operator are not normal because it is identity, yes? We first shift to the right, put the 0 on the first place, and then come back to the left. And another we shift to the left, then come back to the right and put on the first place 0. It is a projector. It is a projector. It is a projector on the orthogonal complement to the first basis vector. I denote in this way. Is it clear? So this is projector on X. This is all sub-index. It is sub-index. The orthogonal complement to the first basis vector. Gives us this. So this is examples of, and for properties for the normal operators are nearest to the self-adjoint. They are almost self-adjoint operators. We later construct the model of self-adjoint operator. Self-adjoint operators is equivalent to operator for multiplication on some real-valued function. Normal operators is equivalent to operator of multiplication on some complex valued functions. That's all. And some properties of normal operators. We need it for prove some theorem on spectrum of operators. So properties of normal operator. Is it clear? The shift in scalar operator preserves the normality. So this operator is normal. So shift on scalar operator is just direct calculation. And second, And of course, the notion of normal operator is only correct only in Hilbert space, because you can't define the multiplication of operator with its Banach adjoint, because they live in different spaces. It is not easy, it is possible to prove it. The main way in Hilbert space, write the norm in a square of the norm and then rewrite the square norm as scalar product. Oh, it is clear.
Yeah, this one's clear. Just want to go back a little bit. Why is the second one considered as a projector? Why it's not the same as the first one?
What?
Why isn't it the same as the first one? I mean, if we go right and then come back left, we'll get back to 0. If we went left and then come back to the right, we'll get back again to 0.
No. So, just the definition of this operator. If I first change to the right, I obtain this, and then turn this, shift this sequence to the left. You take away this 0, you obtain the identity operator. But if you take first this operator, shift to the left, and then use the shifting to the right for this operator, and you put the 0, 0 component for this sequence on the first place. So you obtain 0, x2, x3, and so on. So they're different. I don't understand what is the question. So why it is projector? Because this is the composition of our space L2 and 2 subspaces. It's one-dimensional, so it's close, it's complementary, orthogonal. So this is just this all vectors of such type.
Thank you, sir.
So we need to calculate it, yes? I just one hint. Write it in the following way. I just shorter to finish. By definition of adjoint operator, you put it here. Then you change the order because it is normal. Change the order here. And then put operator here. And you obtain this. That's all. And once more, let's consider so-called for self-adjoint operator. Of course, what the definition? The definition. Let's consider bounded operator in Hilbert space. Is quadratic form of operator. For arbitrary operator, it is a useless thing. But for self-adjoint operator, quadratic forms describes all property of operators. So in St. Petersburg school, their approach that there are no operators, there are no self-adjoint operators, there are quadratic forms. So you can write anything property of self-adjoint operator by its quadratic form. And if operator is self-adjoint, of course, its quadratic form is real. Yes? If A is self-adjoint, then its quadratic form is real for any x from H. We obtain quadratic form when we use different vectors x. I think it's clear, yeah?
In physics, the quadratic form is the expectation value of this.
I think it's not a physical expectation value, it is maybe in probability theory. Yes, but quadratic form is very convenient instrument. It is why this, because by definition of self-adjoints you can put it here, yes? Because it is self-adjoint, we needed to put here star, yes? It is the same operator. But then by definition of, by axiomatics of scalar product, you change the orders of arguments, then you must take a conjugate value of this scalar product. So we obtain that the value equals to conjugate value, so it is real. So it is real. In complex spaces, you work with bounded operator, if quadratic form is real, the operator is self-adjoint in complex space. Because in real space, for any operator, quadratic form is real by definition of the real space, of scalar product. Because scalar product gives the values from the field. So in complex space, if quadratic form is real and operator is bounded, then it is self-adjoint. For unbounded situation, it is only symmetric operator. Convenient theorem of the for property of quadratic form of self-adjoint operator. If you remember, we defined the norm of operator. We can calculate the norm of operator as supremum of semi-square linear form on two spheres. For self-adjoint operators, you can take the supremum of quadratic form on the unit sphere. So theorem. In Hilbert space. First, one step is, let's define this number as C for shortness. So supremum of quadratic form is C, the norm of operator A is norm of the operator A. Our goal to prove that norm of operator coincides with C, capital. Yeah? First is for arbitrary operator, for arbitrary bounded operator. Cauchy-Bunyakovsky inequality and then multiplicative inequality. And we immediately obtain that C, yes, we take the supremum for Lx with unit norm and we obtain this inequality. So you see we have no self-adjoints. We need no self-adjoints in this inequality. And you can, moreover, take the Jordan blocks 2 by 2 and zeros on the diagonal. You can check that the supremum of quadratic form less than norm for Jordan blocks. But for now operator is self-adjoint. So let's consider such two quadratic forms. There are difference of two quadratic forms, yes? First quadratic form of the sum of two vectors. And second is quadratic form on the difference of two vectors. What you can say about this value? Let's take away brackets, yeah? AXX plus AXY plus AYX plus AY, y. minus AXX, here AX minus Y plus AXY plus again minus minus, two minuses. So AYX and here three minuses. 1, 2, 3. So minus AYY. So this go away, this go away. What about the middle terms? These are twice. Yes? But operator is self-adjoint. Operator is self-adjoint, just I only this simplified. I rewrite it in another form. By self-adjointness, it equals to this. And then by axiomatic of scalar products, it equals to the conjugate. So you have a sum of this and this. You have the sum of dual conjugate numbers. So it is twice the real part. And we have one and second terms. So we have that it is for self-adjoint operator. Here we use the property of self-adjoint operator. Okay.
Was it 4 times you wrote?
4 times real part, yes. Because these 2 times and here again 2 times. So we have 4 times real parts.
Okay.
I write it in the following way for this is capital minus. Let's try to estimate the absolute value. Is it clear that for any operator, we use self-adjoint operator, that quadratic form can be estimated in the following way? I remind that C capital is the supremum on the unit sphere. So because it is supremum, it have up estimations. Yes? So we can, it's when you see such object, what identity must be applied? Parallelogram. So the diagonals and they equal to the sum of squares of all edges of the parallelogram. So it is twice. Yes. And what we need to choose the y, vector y, in a proper way, in a good way. Main idea, I want that the norm of y equals to norm of x. To twice these values, first. Second, I want to choose such y that this was a real. Without not real part, but this was real. So I take y equals ax divided on a norm of ax multiplicated of norm x. What is the norm of y? The norm of this vector is 1. And I multiplied it on norm x. So the norm of y equals to norm x. And if I put x, y here, so I obtain the scalar product ax on ax with some numbers. So it is real. So we immediately obtain what we obtain. AX on AX. It is AX squared, but I divide it on AX in the first power. And put y here, and norm y is equal to norm x, so we're again twice. And take the supremum all over x with unit norm, we obtain it. I think we obtain the inverse inequality. And to work in following further for self-adjoint operators, so we just remind we have some good properties of a quadratic form of bounded self-adjoint operator. Second, who knows? Second question: who knows the Banach-Stengauss theorem? Anybody?
Uniform boundedness.
Yes, it's principle of uniform boundedness. No? So, what's the theorem? Banach-Stengauss. First space is Banach, is complete. Second, not obvious complete, only not. And we have a family of operators. So A alpha, alpha from some set of indexes, lambda capital, family of operators, bounded. So and for any x, you can estimate the result of action of operator with some constants which do not depend on alpha. You see, the operator can depend on alpha, the indexes. But the estimation of norm, the estimation of do not depends, it depends only on this x. It depends only on this x. Do not depend on alpha. Depend on alpha. It is an important thing. Then they are uniformly bounded. They are uniformly bounded. The proof of this theorem is not very difficult, but in program it stays as without proof. If somebody wants to understand how it proof, I can explain it in private. But in program it stays as without proof. But some application of this theorem, for example, some application of this theorem. How you can define the bounded set in norm space? The bounded set in norm space. M lies in X. X is normed space, and you want defined bounded. It lies in some ball. It lies in some ball, or there exists some constant C positive that for any x from M, the norm of x less than C. It's just the same. This set lies in a ball with radius C. how you can define the weakly bounded set.
I think like in a topological vector space with a general
No, we work in norm space, so defined it with the help of the notions of the norm space. Is weakly bounded set.
maybe if it's bounded with respect
Weakly, if we meet the word weak, so you must use functionals. So it means that for any f, we know that the dual space is not empty. It is good space. The result of action of functional element x from M can be estimated by constant which do not depends on x. It depends only on functional. Here constant do not depend on x. It's uniform constant. So this constant is uniform with respect with x, with the set M. It depends on functional, but it not depends on M. Depends only on functional. So we introduce the notion of weakly bounded set. What is the difference between bounded set and weakly bounded set? It may be surprising fact, but then no difference. It is one of the rarest examples when weak notion coincide with the usual notion. So it is easy to see first, if M is bounded, then M is weakly bounded. Why? Because norm x less than c by definition. So you obtain that it is c multiplied on the normal function. So this is your constant c of f, which depends only on functionals. Yes? And statement, it is not a theorem, it is some notation, that the inverse implication is very true. If M is weakly bounded, is bounded. Why? A proof. Let us consider the family of functionals f sub x from x to c, and small index x is from M. We consider such functions from this space. They are from this space. How we define these families? How we define each member of this family? For any f from x star, f x small on f defined as canonical embedding. But here we consider not any x, but only x from M. By corollary free from Banach theorem, we know that the norm of this functional equals to what? Then it's equals to norm x. So for any x, fx is bounded. It is the first assumption from theorem Banach-Steinhaus. All elements of your family of operators, but functionals is partial case of operators, must be bounded. And second, by weakly boundedness of M, you can write this estimation. And this do not depends on the index. We have index is x. And this is value is not depends on x. So by Banach-Steinhaus theorem, what you can conclude? By Banach-Steinhaus theorem, the supreme of norm of fx all over set of indexes, and set of indexes are from M, is less than infinity. But this value just equal to the norm of x. So we obtain that our set M is bounded. Yes? Is bounded. Okay. And more interesting fact and more useful for us, for our lectures, for quantum mechanics, for example. The typical operators for quantum mechanics. For example, operators of coordinate, yes, or impulse, but they are unbounded. They are unbounded. But we define this as operators in L2, for example, L2R or L2R3. What properties gives us unboundedness? So unboundedness operators, if operator is symmetric, for example, I will show that in this situation, operator must have domain. It can be defined on all space, cannot be defined on all space. It must be defined on some domain. For example, if you consider operator AX AF equals XFX, it is operator of multiplication, so-called operator of coordinate. You can define it only if F in L2 are, for example, one-dimensional situation when particle fly in one line. Then XF, you can consider this operator from L2 to L2. Because XF possible do not belong to L2. So you must describe the domain of operator. Domain of operator, A, this is such function f from L2 such that XF belongs to L2. If you want to consider this operator from L2 to L2. And it is a typical situation for unbounded operator. So theorem, just clear the blackboard. Oh. Like this. Hellinger-Toeplitz theorem. Hellinger-Toeplitz theorem. Let H is Hilbert space. And A is linear, and for any x, y from H, the following equality is valid. For unbounded operators, it is not a self-adjoint operator. Later we will discuss it in details, but for unbounded operators, it is not a definition of a self-adjoint operator. Because as I say, the unbounded operator must have domain. Maybe this adjoint operator, there are possible situations when a joint operator has more larger domain. The larger domain. It's so-called symmetric operators. Then A is bounded. So if you define your operator on all space with this property, it must be bounded. So inverse, if you have, for example, this operator has this property. Yes, it is clear. Because x is a real function. So for this operator, you easily can check fg equals integral x f g x conjugate dx. You can rewrite it as fx x g x dx equals to fag. So you see that this operator has this property. But we know that it's unbounded because the result of action of operator, the image of operator in the general situation is not from space L2. So by Hellinger Toeplitz theorem, it must have a domain. Yes? So this is possible. If you consider, if this E and your operator is unbounded, the Hellinger Toeplitz theorem forbids it. Yes, it is impossible. So why the many operators from quantum mechanics are unbounded? So proof. By contradiction. By contradiction. Let it is unbounded. Then what we can construct? What exists? There is a sequence xn such that the norm xn equals to 1 and axn by norm greater or equal to n. Yes? It is unbounded, gives us unbounded sequence of values on unit sphere. Let's consider functionals. I think it's clear that it is linear functional. Yes. Yeah? What we can say about the norm of each functional? Take this property. Take this property. And write it as and by Cauchy inequality so it is bounded with it has self norm, something which depends on n, but it is bounded. Your operator is defined for any. your operator is defined for any vectors, so this vector AXN is defined and has finite norm. In Banach-Stengauss theorem, we must have a family of bounded operators. Functional is a particular case of operator. So we have a family, countable many, set of functions, linear bounded. But with this property, you can obtain another estimation in this order. And we take xn with the unit norm. So the last estimation is we obtain by this value. And you see that this value is not depends on n. It does not depend on index. What you can say with the help Banach-Stengauss theorem? By Banach-Stengauss theorem, you can say that they are uniformly bounded. So they are uniformly bounded. So supremum of all norms is bounded. Supremum of all index n.
But sir, in this case, A is normal.
No, any. You have linear operator only with such it's linear, yes. Only linear without boundedness. Only linear operators without any.
For this property.
But we have such properties. So
Exactly, to switch the place of A. Is
Yes.
it that it is related to normal operators?
no.
If it's linear and non-normal operators.
It is almost self-adjoint.
Yes.
Almost self-adjoint. It will be self-adjoint if the domain of operator A and the domain of operator A star are the same. But if you have this property and prove that it is bounded, it immediately changes to the self-adjoint operator. With these two properties, you can name this self-adjoint. But in general situations, it's only symmetric operators. Symmetric is a wider class of self-adjoint operators. Any self-adjoint operator is symmetric, but in inverse is not true. For example, operator of coordinate in quantum mechanics, multiplication on x and L2, is unbounded and self-adjoint. So finish the proof, and I show another example about the operator of impulse. So Banach-Stengauss theorem says us that the supremum of all norms are bounded. Yes, are fine. So, but we have this property. I put this vector in this representation. X like this. It equals AXN divided the norm AXN multiplied on AXN and scalar product. It equals to AXN less or greater than n. On the unit sphere, these all elements has unit norm. It contradicts with what?
Uniform boundedness.
With this. It contradicts with this. Because you can obtain the norm of n larger than n. And this is contradiction to this Banach-Stengel theory. And when we start investigate, when we start to learn the unbounded operator in more details, we consider the following operator. I consider this space not real axis by the interval 0, 1. And I consider operator AF equals EF prime. It's just up to the Planck constant, it's impulse. Yes? And we know that this operator is unbounded. Because if you apply it to the sine, the norm of sine nx equals square root of 2 and L2 0, 1. But A sine goes to cosine. Cosine has the same norm, but you have a constant n. P nx, pi nx. So it is has this. So if this set was bounded, this set is unbounded. So your operator is unbounded. And it's easy to see that A, F, G, but what is the domain of operator? Where, on what space you can take a derivative? The functions from L2 have no derivative, yes? In general situation. But if you take the Sobolev space, its derivative lies in L2. But additional, I take two additional sums, boundary conditions. It's easy to see integrate by parts. Let's integrate by parts. EFG 0, 1 minus EFG prime x dx. This is 0 by boundary conditions. And then put the imaginary unit outside the conjugation. You immediately obtain this. But we know, we show that this operator is unbounded. By Hellinger theorem, Hellinger-Toeplitz theorem, it must have domain. Because it's unbounded and has this property. And this operator is not self-adjoint. Because very strict, this assumption is very strict, this condition. The main idea of construction of self-adjoint extension, it is symmetric operator. The main idea of self-adjoint extension of symmetric operators is find such domain for symmetric operator that the domain of operator coincides with the domain of adjoint operator. Because for unbounded operator we have domains. You see that the adjoint operator by this formula looks like A. It is derivative with multiplication on imaginary unit. But the adjoint operator has another domain. We'll show it later. It's not okay. So I give you two applications of Banach-Stengel theorem. The equivalence of boundedness of set and weakly boundedness of set, and Hellinger theorem, Hellinger-Toeplitz theorem, which is important for quantum mechanics, which show us that operators must have domains, unbounded operators. So in quantum mechanics you can consider bounded operator. For example, the operator of spin is bounded operator. It's the operator by matrix 2 by 2 in two-dimensional space. But operator, this operator is unbounded. Oh, we consider it on a home task problem.